When we look up at the night sky, especially through the powerful eyes of our newest telescopes, we see something truly magnificent. We see galaxies swirling with billions of stars, vast clouds of gas where new suns are being born, and light that has traveled for billions of years just to reach us. It's an image of immense beauty and scale. You might think, with all this technology and all the brilliant minds studying the cosmos, that we must have it all figured out by now. But the truth is, the more we learn about the universe, the more we realize how little we actually know. It's a wonderful, humbling thought. The universe is full of mysteries that we are only just beginning to grasp. For every question we answer, it seems 10 more pop up in its place. The biggest questions of all are about the very nature of everything. What is the universe made of? How did it begin? And where is it all going? We have theories, of course. We have a standard model of cosmology that has worked brilliantly for decades. But recent discoveries have started to show cracks in that beautiful model, suggesting that our understanding is far from complete. It's like we've opened a door to a vast room, but we can only see a tiny corner of it. One of the most fundamental things we thought we knew was how fast the universe is expanding. Imagine you're baking a loaf of raisin bread. As the dough rises, all the raisins move away from each other. That's a bit like our universe. Ever since the Big Bang, space itself has been stretching, carrying all the galaxies along with it. The speed of this expansion is called the Hubble constant. Measuring it accurately is one of the most important jobs in all of cosmology because it helps us figure out the age and the ultimate fate of our universe. Getting it right is absolutely crucial. But here's the problem: we can't seem to get it right. Or rather, different ways of measuring it give us different answers. This disagreement, which scientists now call the Hubble tension, has become a major crisis in cosmology. It's not a small error that might go away with better data. The measurements are now so precise that the two main results simply cannot both be correct. It's a profound disagreement that tells us something fundamental about our understanding of the universe is wrong. We are missing a piece of the puzzle, and it's a very big piece indeed. So, how do we measure something as vast as the universe's expansion? Scientists have two main methods, and this is where the trouble starts. The first method is to look at the universe nearby. To do this, astronomers build something called a cosmic distance ladder. They start by measuring the distance to nearby stars, like Cepheid variables, which pulse at a rate related to their true brightness. By knowing how bright they really are, we can tell how far away they are. They then use these stars to calibrate the brightness of more distant objects, like exploding stars called Type Ia supernovae, which can be seen across the universe. Using this ladder method with powerful telescopes like Hubble and the James Webb Space Telescope, astronomers have measured the expansion rate to be about 73 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light-years. This means a galaxy 1 megaparsec away is racing away from us at 73 kilometers per second. This is the local measurement based on what we see happening in the universe today. It's a very precise number, built on decades of careful observation and cross-checking. It seems solid. The second method looks back in time, all the way to the baby universe. Scientists study the faint afterglow of the Big Bang, called the cosmic microwave background, or CMB. This ancient light, captured by missions like the Planck satellite, contains a snapshot of the universe when it was only 380,000 years old. By studying the patterns in this light and applying our standard model of physics, we can predict how the universe should have evolved and how fast it should be expanding today. This method gives us a completely different answer. The prediction from the early universe tells us the expansion rate should be much slower, around 67 or 68 kilometers per second per megaparsec. This isn't a small difference. two methods, both incredibly precise, are in direct conflict. It's as if you measured your child's height and then used their baby shoes to predict how tall they should be, only to find the prediction is off by several inches. Something is wrong, either with our measurements or, more excitingly, with our understanding of how a child or a universe grows up. Faced with this puzzle, scientists are racing to find an explanation. One idea, proposed in 2025, is that we might just be in a strange part of the universe. Perhaps we live in a giant cosmic void, a region of space that is much less dense than average. If our galaxy is inside a huge bubble that is emptier than the space around it, then the stronger gravity from the denser regions outside the bubble would pull everything away from us faster. This would make the local expansion look faster than the true average expansion of the entire universe, which would neatly explain the discrepancy. Another approach is to find entirely new ways to measure the expansion, independent of the first two methods. Recently, astronomers have started using mysterious signals from deep space called fast radio bursts, or FRBs. These are incredibly bright, millisecond-long flashes of radio waves from distant galaxies. As these bursts travel across the cosmos, their signal gets stretched by the expansion of space. By studying how much they are stretched, we can calculate the distance they have traveled. A 2025 study using nearly 100 of these FRBs gave a Hubble constant value that sits right in the middle of the other two, not quite solving the problem, but offering a promising new tool. But the Hubble tension is not our only cosmic headache. The standard model of cosmology tells us that everything we can see, all the stars, planets, and galaxies, makes up less than 5% of the universe. The rest is made of two invisible ingredients, dark matter and dark energy. Dark matter is the mysterious stuff whose extra gravity holds galaxies together, stopping them from flying apart. We know it's there because we can see its gravitational effects, but we have no idea what it is. It doesn't shine, it doesn't reflect light, it's just dark. Then there's dark energy, which is even stranger. It's the force that is causing the expansion of the universe to speed up, and it makes up about 68% of everything. We thought it was a constant force, but recent results from the dark energy spectroscopic instrument suggest it might be changing over time. And if dark energy isn't constant, it complicates our models even further and actually makes the Hubble tension worse. It seems the more we look into the dark, the more mysteries we find waiting for us. So we find ourselves in a strange but wonderful position. We have built incredible instruments that can peer back to the dawn of time and measure the cosmos with astonishing precision. Yet, these same instruments have revealed that our best theories are incomplete. We don't know what 95% of the universe is made of, and we can't agree on how fast it's all moving apart. This might sound like a failure, but it's exactly the opposite. This is what science is all about. It's not a collection of facts in a textbook. It's a messy, exciting, and deeply human process of discovery. The Hubble tension, the mystery of dark matter, the enigma of dark energy. These are not problems that signal the end of cosmology. They are signposts pointing the way towards a new, deeper understanding of reality. They suggest that there is new physics waiting to be discovered, ideas as revolutionary as Einstein's theory of relativity was a century ago. Every time in history that a trusted scientific model has broken down, it has led to a breakthrough. We are living through one of those moments right now, on the frontier of human knowledge. This is what makes being a scientist, or even just someone interested in science, so thrilling. It's the not knowing that drives us forward. It's the puzzle that keeps us searching. The universe isn't a closed book that we have almost finished reading. It's a story that is still being written, and we are lucky enough to be able to read the first few pages. The fact that the universe is more complex, more surprising, and more mysterious than we ever imagined isn't a cause for despair, it's a cause for wonder. And so we continue to look up, we build bigger telescopes, we design cleverer experiments, and we listen for whispers from the cosmos. We don't know what answers we will find. We might solve the Hubble tension only to uncover an even bigger puzzle. But that is the joy of it. The universe doesn't give up its secrets easily, and the quest to understand our place within this vast, beautiful, and mysterious cosmos is the most magnificent adventure of all. The journey is everything.